In the previous video, we discussed the process involved in order to statically balance a rotating system. In this tutorial, we're going to be looking at balancing a similar system, but in this example, we need to achieve both static and dynamic equilibrium in order to balance the system. The reason being is if this system is rotating, then not only does this system need to balance in the front plane, but it also needs to balance in 3 dimensions. And this will become more apparent as we go through this tutorial. Referring to the diagram then, we have 2 masses positioned. We have mass B and mass C. Now we know the magnitudes of each of those masses, 4.5 and 2.5 kilograms respectively, and we also know their distance from the neutral axis. We have 20 millimeters and 50 millimeters on the front view diagram for the assembly. And we also know their angular positions, 45 degrees from the horizontal for B and minus 60 degrees from the horizontal for C. Now, in addition to that, we know their positions along the length of this rotating shaft. We can see that B is placed 80 millimeters from the far end, or point A, and we can see that C is positioned 150 millimeters. We have 80 millimeters plus 70 millimeters, again from point A. Now, what we need to do in this instance is we need to add 2 additional masses. We need to add a mass in plane A, and we need to add a mass in plane D. And we need to position them such that we achieve static and dynamic equilibrium. Now you'll notice in the bottom left-hand corner that we don't yet know the size or the magnitude of mass A, but we know that it's going to be positioned on a radius of 45 millimeters. The same is true for mass D. We don't know the magnitude or the size of mass D, but once again we do know that we want it to be positioned at a distance of 45 millimeters from the neutral axis, or on a radius of 45 millimeters. So what we see here is that we have 2 unknowns. And so the way that we're going to approach this is by this time creating 2 vector diagrams. One of our vector diagrams is going to be for the mass times the radius once again. And the second of our vector diagrams is going to be for the mass times the radius times the length or the distance from point A. We'll just label point A on our diagram. Now the reason why we're doing that will become apparent in a moment. So let's construct a table. We have mass A, we have mass B, mass C, mass D. We don't yet know the magnitude of mass A, so we'll just call it M subscript A for the time being, but we do know its radius is 45 millimeters. Therefore, the mass times the radius for mass A is 45 times MA. Now, this is the reason why this approach is useful, is because when we move to the next column for mass A, we have M times R times L, where L is the position from point A. Well, we've already said that we're going to be placing mass A somewhere in plane A, therefore that length L is going to be 0, meaning M times R times L for mass A is going to be 0. When we come to construct the MRL vector diagram, mass A will not need to be represented because its magnitude is 0. Okay, let's repeat for mass B. We have a mass of 4.5 kilograms at a radius of 20 millimeters. Now once again we're going to work in millimeters. So long as we're consistent here, we can use millimeters for constructing our vector diagrams. 4.5 times 20 is just 90. And in our third column then, for mass B, we have the magnitude of the mass, 4.5, times the radius of 20, which gives us our 90, times our distance from A, referring to the diagram here, which is 80 millimeters. 90 times 80 equals 7,200. Repeating for mass C has a magnitude of 2.5 kilograms, but it's placed at a radius of 50. Well, 50 times 2.5 equals 125. And moving to our third column, we have 125 times its distance from A. Well, as we mentioned earlier, the distance from A is 80 plus 70, or 150. 125 times 150 equals 18750. And finally we have mass D. Mass D has an unknown magnitude, but we know it's being placed on a radius of 45. So for the same reasons as for mass A, we're going to get 45 md. Moving to the final column for mass D then, we can see that mass D is at a position of 250 millimeters from point A. We previously had 150 millimeters to mass C, and then we need to add on an additional 100 millimeters, giving us 250 millimeters in total. 250 times 45 then equals 11,250 md. Note that 11,250 there is the radius times the length. We have m times r times l. So we're going to construct a vector diagram, first of all, using our MRL values in the final column there. And in doing so, we're going to be able to determine the magnitude of mass D and its position. So let's do that now for mass D. First of all, we have mass B, and we see that mass B is positioned at 45 degrees from the horizontal. So we know our angle is going to be 45 degrees. Its magnitude is 7200. Now once again, this doesn't need to be to scale, but we want it to roughly represent the quantities as it will make it easier to visualise our resultant and our equilibrium. So the length of that line there is 7200. Added to that, we have the MRL line, this time for mass C. We know it's acting at minus 60 degrees from the horizontal, and its length is roughly 2.5 times the length of our previous vector in this direction here. The magnitude of that line is 18750. So now what we can see then is that the resultant, which connects the start of the first vector to the end of the second vector, acts in this direction here. Now, as we mentioned previously, our equilibrium is going to have the same magnitude, but the opposite direction. Let's add some angles on here. We have an internal angle here, 45 degrees. And we have an internal angle here of 60 degrees. So now we can use trigonometry to determine the sum of our x components. The x component of our first vector is this face here, 7200 cos 45. And the x component of our second vector is also positive here, going from left to right, and its magnitude is 18750 cos 60. Giving us a sum of our x components then equal to 14466.2. Let's repeat for our y components. Our y components, well, we can see the first vector, vector b, has a positive y component, the magnitude of which is 7200 sine of 45. But this time we can see that our second vector, or vector c, has a negative y component. It acts downwards. So this time we need to subtract its magnitude, 18750 sine 60, giving us a sum of our y components equal to minus 11146.8. So now we have the sum of our x components and the sum of our y components for our m times r times l vector diagram. Let's construct a new triangle to represent our resultant, and then we can determine the magnitude of the resultant and the direction of the balancing equilibrium. Okay, so we have a positive x component, 14466.2. But we have a negative y component. That's why our y component's acting downwards there. 1146.8. Now we're going to use Pythagoras' theorem to determine the magnitude of our resultant, which acts in this direction. We're then going to use trigonometry to determine this angle, which I'm going to call theta. And then we can determine the bearing of our equilibrium, which effectively opposes the resultant. Like so. So using Pythagoras' theorem, we know that r squared equals the sum of the square of the two shorter sides. Therefore, r equals the square root of the square of those two shorter sides. We have 14466.2 squared plus 11146.8 squared, giving us a resultant this time equal to 18262.6. And before we discuss the significance of that, let's also work out our angle theta. Theta is tan to the minus 1 of opposite. Well, opposite the angle, we have the 11146.8 over adjacent, and our adjacent is 14466.2. Gives us an angle theta equal to 37.6 degrees. Now, if we refer to our diagram, we can see that the angle theta is not being expressed as a bearing. And in actual fact, we want the bearing for the equilibrium. So if I just add to my sketch here, a horizontal line, we know that the opposite angle here is going to be the same as theta, 37.6. However, the bearing that we need to determine is actually this angle here. Now, as the angles on a straight line add up to 180, the bearing here is just going to be 180 minus 37.6, which equals 142.4 degrees. So the angle indicated there is 142.4 degrees. But what we haven't yet done is determine the magnitude of our mass m. All we have is a resultant vector here of 18262.6. Well, this resultant here is equivalent to 11250 md. Recall that we constructed the vector diagram for MRL, and that resultant was for vector D. And vector D, we said, had a magnitude of 11250 times the mass of D. So finishing this up to find mass D, we know that the resultant equals 11250 md. Therefore, md is the resultant of 18262.6 divided by 11250, giving us a mass of D equal to 1.62 kilograms. So let's add mass D to our diagram. We know that it's on a bearing of 142 degrees. We know it has a magnitude of 1.62 kilograms. And we know that it's placed a distance of 45 millimeters from the neutral axis. So mass D then is going to appear somewhere around here. But we haven't quite finished because we've determined the magnitude and position of mass D, but we haven't yet determined the magnitude and the position of mass A. So let's clear some space and then we're going to go through the next steps in order to determine the magnitude and position of mass A. Okay, so in order to determine mass A then, we're going to construct a second vector diagram, except this time we're going to construct the vector diagram for mass times radius, as we did in the previous tutorial. We can now make one update to our table as well, because we know that the magnitude of MD is 1.62, and 45 times 1.62 equals 73, accurate to the nearest whole number. So I'm going to replace 45 MD with our known value now of 73. So let's begin constructing our vector diagram then. This time I'm going to start with vectors B, C and D, and the resultant vector can then be used to determine the mass of A. So B has a value of 90 at 45 degrees. Again, I'm not drawing this to scale, but I want the proportions to look roughly right. So B, 45 degrees, magnitude 90. C, angle minus 60 degrees, magnitude 125, so slightly longer than our previous vector. 1, 2, 5. Vector D, we can see has a magnitude of 73, and we know its angle to be 37.6 degrees from the horizontal here. Recall that that internal angle there corresponds with a bearing of 142.4 degrees. So this is the shortest of our three vectors. With a magnitude of 73. Our resultant vector then is going to join the start of the first vector to the end of the last vector. Now, the way that we determine its magnitude, once again, is first of all to determine the sum of our x components and the sum of our y components. So let's add a couple of angles on here. We have 45 degrees for vector B. We have an angle here of 60 degrees for vector C, and an angle here of 37.6 degrees for vector D. So let's find the sum of our x components and the sum of our y components then. The sum of the x components is the x component of vector B, or the x component is going to be 90 cos 45. Now to that we're adding the x component of vector C. Now notice once again that the x component of vector C is positive. So we're adding 125 cos 60. But notice that the x component of our final vector, vector D, is negative. Therefore we need to subtract its magnitude of 73 times cos of the angle 37.6. Giving us a sum of our x components then equal to 68.30. And let's repeat for our y components. We can see that vector B, our first vector, has a positive y component. So we have 90 sine 45. We can see that vector C, or our second vector, actually has a negative y component. It's acting downwards. So this time we need to subtract 125 sine of the angle, or sine 60 in this case. And finally, vector D has a positive y component because it's acting upwards, like so. So we're adding 73 sine 37.6, giving us a sum of our y components then equal to minus 0.1. I'm just going to sketch the new vector diagram for completeness, and then we'll determine the magnitude of our resultant and the angle or the direction of our equilibrium. Okay, so referring to our new vector diagram then, we can see we have an x component which is positive and has a magnitude of 68.3, and we have a y component that's negative but only has a magnitude of 0.1. Our resultant then is going to act in this direction here, meaning our equilibrium is going to act in the opposite direction, but it's going to share the same magnitude. The magnitude of the resultant is the square root of the sum of the square of the two shorter sides. So here we have 68.3 squared, we have 0.1 squared, giving us a resultant this time equal to 68.3. Now we can already see that our internal angle here, theta, is going to be negligible, but we'll calculate it anyway for completeness. Tan theta equals opposite over adjacent, therefore theta is tan to the minus 1. Opposite, 0.1, over adjacent, 68.3, giving us a theta value equal to 0.1 degrees. So we can see that the resultant is almost horizontal, acting left to right with a bearing of 0. Therefore our equilibrium then, and again just for completeness, our angle of our equilibrium here is also going to be theta. Therefore the bearing, reading from 3 o'clock and anti-clockwise, is going to be 180 minus theta, or in this case 180 minus 0.1, giving us a bearing of 179.9 degrees. So we still have one thing left to calculate, and what we need to calculate is our mass Ma. Now from the vector diagram, we know that 45 Ma is equivalent to 68.3. We obtained that from our MR vector diagram. And we found that the magnitude of the line representing 45 Ma had a magnitude of 68.3. So we can write the following in the bottom left-hand corner. R equals 45 Ma. Ma equals R over 45, or in this case, 68.3 over 45, which gives us a mass A equal to 1.52 kilograms. So adding our value underneath our diagram, we have A equals 1.52 kilograms at 45 millimeters. We also know that that acts at an angle or a bearing of 179.9 degrees. So let's go ahead and add that to our diagram. We have a bearing of 179.9 degrees. We have a length of 45 millimeters. And we have a mass of magnitude 1.52 kilograms. So now we know the magnitude and position of mass A on plane A and the magnitude and position of mass D on plane D in order to put this rotating system into both static and dynamic equilibrium, thus fully balancing this rotating system.